In this video, we introduce our work, Assistive Navigation via Conditional Instruction Generation. Current embodied vision and language navigation systems are mostly studied in static indoor conditions. The utility of vision and language navigation systems in assisting blind navigators during complex and dynamic navigation has not been explored. There are two key challenges hindering the development of learning-based assistive navigation systems. First, it's difficult and costly to conduct real-world user studies. Second, compared to current VLN tasks, the system requires more elaborate modeling of the information needs of the blind navigator. Therefore, developing learning-based assistive systems for maintaining the real-time awareness of a blind agent remains a grand challenge. We collected a real-world multimodal benchmark, with diverse interactions between experts and blind navigators, during navigation in dynamic urban settings. However, real-world data collection is inherently limited with issues of safety, cost, and data diversity. We therefore supplement our analysis with simulation environment based on the Carla simulator. Compared to other photorealistic navigation-centered datasets, our datasets analyze contextual cues and guidance instructions for blind navigators. We also emphasize outdoor navigation involving dynamic obstacles. We then use the data to train an imitation model that learns to generate instructional sentences to collaborate with a person with visual impairment on navigation in urban environments. Our real-world dataset consists of synchronized multimodal camera and sensor data, together with their corresponding in-situ expert instructional guidance. For the study, we recruited blind individuals and orientation and mobility guides through a local blind individual services center. We asked the blind participants to navigate an unfamiliar planned route through a business district, with typical weekday traffic, helped by remote orientation mobility guidance. While Carla is typically used for autonomous driving development, we modify the environment to collect instructional guidance and a sidewalk pedestrian perspective in various weathers and towns. We use the large synthetic dataset to rigorously analyze model limitations across ample standardized data and more diverse visual conditions such as new towns and harsh weathers. We consider the task of learning instruction synthesis from observation space O, which comprising a front view camera image I, the start position and heading of the instruction follower P0, and a planned route P, which specifies waypoints towards a goal position. Our goal is to obtain a mapping function F, parameterized by theta, for generating a sequence of instructional tokens W from observations. Our instruction generation model can be trained by minimizing a sequence prediction cross-entropy loss, L, between the prediction and expert's instructions given observations. Our model comprises three main components. First, we use a visual semantics feature extractor to extract and generate region features and object tags. We then design a goal-conditional module, which extracts goal-based features, and leverages navigation commands generated from a future planned path, to ease the learning of alignment among modalities. In the training process, ground truth instructions are masked, and are used together with object tags and commands to generate word embeddings. Altogether, we aggregate the inputs with a state-of-the-art BERT language generation module, to generate intuitive navigation instructions. Note that the masked instruction are only used in training process, and during inference, the model sequentially infers instructional words without access to ground truth. For results, our model demonstrates superior instruction generation results in both real-world and simulation setting, compared to Oscar and hard attention LSTM. Our model also achieves high improvement in terms of success rate, route completion and navigation errors, in task-based evaluation in simulation, indicating the effectiveness of the proposed method. Here we show some qualitative result from evaluating on our real-world and simulation dataset. We show our interactive experiment design that leveraged simulation environment to perform a user study with participants navigating routes in a blind simulation. To simulate blind navigation, the participants are shown the user view, with no image, only course orientation with noise and collision information. The participants controls the simulated walker by standard keyboard controls. The instructions shown on the left are provided to the participants based on query, and are either generated by our procedural process or sampled from the proposed model. We can therefore directly evaluate the ability of the model to guide in complex, dynamic, and previously unseen test settings. Thank you for watching.